My name is Saeed Azad, and I'm currently a postdoc at Colorado State University. In this presentation, I will briefly discuss our article, which will also be presented in person at the IDETC 2022 conference. Allow me to start by giving you a very brief overview of control co-design, or CCD. CCD refers to an integrated consideration of the physical and control system design through optimization in order to improve the performance of the system. As we step into developing more modern and emerging dynamic systems, control co-design methods become more and more relevant. However, the focus of a large portion of CCD literature has been on deterministic cases. Those are situations where no uncertainties are present. However, we know that for any realistic situation, there are some elements of the CCD problem that are inherently uncertain or they're not entirely known. And we refer to both of these cases as uncertainties. The problem is that if we overlook the impact of such uncertainties, the CCD solution may no longer be effective for realistic scenarios. In a CCD problem, uncertainties may stem from various sources. For example, plant optimization variables may be uncertain due to imperfect manufacturing processes. The problem data may be uncertain because we don't have complete information about data such as wind speeds or wave energy densities or earthquake loads. The fidelity of the dynamic model might be another source of uncertainties. Sometimes we simplify dynamics or sometimes we neglect them. Finally, there might be some noise in the control channel that would affect the final CCD solution. These uncertainties transform the CCD problem into an uncertain CCD problem that we refer to as UCCD. There are some limitations currently in the UCCD literature. For example, interpretations associated with robust CCD, a stochastic CCD, and for that matter, any other formulations are not clearly stated. As a result of that, selection of UCCD formulations for specific applications is not always well informed. For example, a lot of research in UCCD area have focused on specific uncertainties from a certain discipline, and they're largely driven by particular solution strategies. However, different UCCD formulations offer different risk measures, and as a result of that, their formal inclusion and representation may inform application-focused UCCD research. The goal of this study is to identify the sources of uncertainties and formalize their inclusion through a universal UCCD problem. From there, we can derive 6 specialized UCCD formulations. Here you can see a deterministic all-at-once CCD formulation. Due to the limited amount of time, I am not going to discuss all of the elements of this formulation, but just note that U refers to the open loop control trajectories. We have a space and we have the vector P, which may entail plant optimization variables or control gains. That's because P is a general variable that refers to time-independent optimization variables. We also have problem data that may include information such as wind speeds and wave energy densities or any other information that is relevant to the problem. Now, before we step into discussing the UCCD formulation, it is important to know the type of variables that we might encounter in a general UCCD problem. Here, you can see 4 types of variables. We might have time-independent and time-dependent deterministic variables. Those are the ones that are illustrated on the top row of the figure. And we might have time-independent and time-dependent uncertain variables. You can also see the mathematical definition of the sets associated with each of these variables. Defining these variables would allow us to better derive the specialized formulations from the universal UCCD formulation. Now, for any variable that is uncertain, that is any variable that belongs to V sub u or T sub u, we can represent them in 3 different ways. We can have a stochastic or probabilistic representation. So in this situation, you can see that in the figure on the left, the blue dots refer to a multivariate Gaussian distribution. We can also have a deterministic representation of uncertainties. In a deterministic representation, no probability measure is available, and uncertainties belong to a crisp set. In the figure on the left, you can see box, ellipsoidal, and hexagonal deterministic sets. Notice that any deterministic set is characterized by a membership function that assigns zeros to all of the non-members and one to all of the members. You can see this membership function in the figure on the right. Finally, there are situations that our knowledge of uncertainties is very limited. In such situations, we can use descriptive and often vague language in order to describe the events of interest, and that language will then be interpreted by experts in the field. The best way to describe such information is through a fuzzy set, which is also can be referred to as possibilistic representation of uncertainties. For any possibilistic or fuzzy set, there is a membership function that assigns a continuum grade of membership to different elements. So for example, instead of having only values of zeros for non-members and ones for all members, we can have values in between. And you can see this illustration on the right, where we have triangular, sigmoid, and Gaussian membership functions associated with fuzzy sets. With all of the preliminaries out of the way, we can discuss the universal UCCD formulation. Notice that this formulation here is described in the probability space, and we can derive various specialized UCCD formulation by the appropriate selection of the objective function and constraints. Notice that here, any uncertain variable is distinguished through the use of tilde. And in addition to that, any time that this tilde is accompanied by a t argument, then that would refer to a stochastic process. Notice that in this equation, we are minimizing the expected value of a composite function, and that composite function is basically a function of the original objective function. The same logic applies to the inequality constraints. Now, this formulation entails a lot of important aspects. The first one is risk. Any UCCD formulation should consider the impact of uncertainties on all of the decisions that we are going to make. And generally, these formulations may be risk neutral or risk averse. In a risk neutral formulation, no measure is taken to hedge against uncertainties, whereas in a risk averse formulation, we are attempting to reduce the risk that is associated with the violation of the constraints. In terms of the decision space, the UCCD formulation must remain balanced and non-biased. In other words, in response to uncertainties, we have to explore both the physical system design and control design in order to make sure that our design, our final solution is robust or reliable. In terms of the objective function, we have to remember that there is no conceptual distinction between the objective function and inequality constraints. In fact, the objective function can be transferred into the vector of inequality constraints through the introduction of a new variable, and we refer to that representation as the epigraph representation. Finally, we might encounter two types of equality constraints in a UCCD problem. We might have type 1 equality constraints. Those are constraints that must be satisfied regardless of the presence of uncertainties. So for example, the dynamics of the system or the laws of physics, they must be satisfied whether or not we have uncertainties in the system. The second type are type 2 constraints, and these cannot be satisfied when uncertainties are present. Finally, there are various formulations and descriptions of inequality constraints. Only a handful of them are shown here in this slide, but notice that any individual description or sometimes their combination may be used to develop various interpretations. In this section, we are going to discuss those. Here, we have a stochastic and expectation UCCD and a stochastic chance constraint UCCD. Notice that a stochastic and expectation is a risk-neutral formulation. Therefore, no measure is taken to hedge against uncertainties, whereas a stochastic chance constraint is a risk-averse formulation. In addition, notice that all of the dynamic system equality constraints and analysis type equality constraints are satisfied almost surely, or AS. That is because of the description of uncertainties that is probabilistic in this sense. On the right side, you can see an illustration associated with uncertain probabilistic constraints, and notice that the red region is referring to the areas where the constraint is violated. Another formulation is probabilistic robust formulation, in which the objective function is a combination of the mean values as well as the standard deviation of the original objective function. The vector of inequality constraints are generally shifted with k sigma in order to acquire a certain level of robustness. In another formulation, we can require the standard deviation of the inequality constraints to remain less than a desired value. Notice that the illustration associated with probabilistic robust UCCD formulation is shown on the right. And remember that probabilistic robust UCCD formulation is also a risk-averse formulation. Finally, we have the worst case robust UCCD. In this case, robustness refers to the situation where the solution remains feasible for all of the realizations of uncertainties that are within an uncertainty set. This resembles a game between the optimizer and the nature, where nature plays an adversarial opponent. In this situation, for any decision that the optimizer makes, the adversarial player tries to perturb and violate constraints as largely as it can. And that results in a semi-infinite problem that can be replaced with the constraint maximization problem. You can see this constraint maximization problem on the right side, and the worst case robust UCCD formulation results in a nested structure. Notice that the optimizer makes a decision in the outermost loop, and then in the inner loop, the adversarial opponent makes a decision to perturb and violate constraints as largely as possible. However, this opponent is limited in its actions to satisfying the laws of physics, dynamic equations, and the uncertainty sets. Here you can see two descriptions that are motivated by fuzzy representation of uncertainties. We can have fuzzy expected value UCCD formulations and possibilistic chance constraint UCCD formulations. A few points of discussion here. First of all, stochastic and robust UCCD are related to each other. In other words, the solution from the worst case robust may approach the solution from the stochastic chance constraint UCCD when the deterministic description of uncertainties is a just representation and the probability of failure associated with a stochastic chance constraint is infinitesimally small. In addition, there are some insights from a stochastic control theory and robust control theory. The stochastic control theory traditionally focuses on idealized processes such as Wiener and Poisson. And in that sense, methods from Ito calculus are generally used. In terms of robust control theory, there is a multitude of methods that have been used to deal with uncertainties. And a lot of those methods encourage the use of closed loop formulations. However, regardless of the control structure, uncertainties propagate into the dynamic system, and it is important for us to be able to capture their impact through the formulations that we introduce in this presentation. Here you can see a notional infinite horizon linear quadratic regulator that is subject to a multitude of uncertainties, and notice that this controller reduces uncertainties in the system response over time. Here are some of the references that I have used in this presentation. Thank you for your attention.